So we've been talking about antiderivatives. We understand our power rule. We understand the antiderivative of basic trig functions rules. So now let's introduce the integral symbol. So this collection of antiderivatives, all right? The collection of antiderivatives represents what we call an indefinite integral. So we have two parts here. We have an integral sign. That means we're just going to find the antiderivative. The function that's in there, that is called my integrand. And then the last piece, this dx, represents my variable of integration. This is called a differential. And it just says, hey, we have the derivative with respect to x. So let's integrate with respect to x. Okay? So the integral symbol really doesn't change much for what we're doing other than our notation. So if I say find the integral of 2x dx, all right? So the integral sign just says, hey, I'm going to go find the antiderivative. And this dx says it's going to be with respect to my variable x. So in this situation, the integral of 2x is x squared. So we would end up with x squared plus c. All right, so this new notation, and we'll talk about it more in future sections, it's just a new way of writing it. So if I said find the integral for secant squared x plus x cubed dx, that would equal, well, the antiderivative of secant squared is tangent, so I have tangent x, and the antiderivative of x cubed, that's going to be 1/4 x to the 4th, because I add 1 to the 3 and then I divide by that value. And we always write plus c, our arbitrary constant. And so just one more example in here. Let's scroll you all the way up. Example, maybe we will find our integral x squared plus 2x minus 5 dx. So that means we're going to find the antiderivative of this polynomial, x squared plus 2x minus 5, which is my integrand right here. And then the dx is just saying, hey, pay attention, we're going to do this with respect to x. And as we move forward in Calc 2, we can have x's and y's in there and be integrating with respect to y, right? So our variables change. But for your purposes, that dx is always going to match the variable in your integrand. So in this case, the antiderivative of x squared is x cubed over 3. The antiderivative of 2x is 2. We've got x squared over 2. And the antiderivative of 5 becomes 5x. We always write plus c. So we could rewrite this and we'd say 1/3 x cubed, the 2's cancel, plus x squared minus 5x plus c. So we have one more problem in this unit, and we're going to deal with an initial value application problem. So we want to remember some previous knowledge, right? All math builds. So remember, when we talk about position and velocity, acceleration, and the jerk, the derivative of position gives us velocity, our rate of change, and the derivative of that velocity gives us acceleration, our rate of change squared, and the derivative of acceleration gives us jerk. okay? So what we have here, we're going to find our displacement, and displacement's just a fancy word for position. So we're going to find our displacement from the antiderivative of velocity. So what we have, suppose this is my velocity given. This is the velocity of a body moving along the s-axis, the position axis. And velocity is equal to 9.8 t minus 3. So you'll notice I have this ds dt is equal to velocity. What does ds dt mean to us? Well, we use s for the position function, so this is the derivative of position, right, with respect to time. And the derivative of position with respect to time is velocity. So all that ds dt is it's a new notation for us. It's called a differential notation. And so we're thinking about velocity is the derivative of position with respect to time. So we're going to do three things in this problem. We're going to find the body's displacement over time given an interval. And we're going to do that 3 times. We have 3 parts. 1, 2, and 3 all have different initial conditions, but they're all talking about the same interval across the course of time from t equals 1 second to t equals 3 seconds. Well, we don't have a unit on time measurement here, so just t equals 1 to 3. So thinking about this for part I, the integral of velocity with respect to time is going to equal my position function. And we need to find position, which tells us displacement. So this means we're going to do the integral of 9.8 t minus 3. We're going to find that integral, or the antiderivative, with respect to the independent variable t. So this becomes 9.8. The integral of t is t squared over 2 minus 3. My integral of 3 just becomes 3t and plus c. And just to refresh, when you are finding the antiderivative or integrating a constant, such as 3, with respect to dx, you want to think about, well, that's 3. How many x's did I have there? 0. 3x to the 0 dx. So that's 3x to the first over 1 plus c. So that's where that x variable comes in. In this case, we're using t as our variable, so that's what we want as our answer there. Okay, so this represents my position function, but it's not an exact position function yet. What we have here is that s of t, 9.8 divided by 2, I've got 4.9 t squared minus 3t plus c. So this is our general position function, but in this situation, we are given an initial condition. We know that the position is 5 when t is equal to 0. So I can use my initial condition, plug those values in, 0 for t and 5 for position, and simplifying that, I get that 5 equals c. So the position function I want to use in this situation is s of t equals 4.9 t squared minus 3t plus 5. All right? So we're then asked to find the displacement from t equals 1 to t equals 3, which we see up there. So t equals 1 to t equals 3, we can find the position at t equals 1, s of 1, and we can find the position at t equals 3. And both of those would be found by just plugging 1 and 3 into this function here. Evaluating it twice, we get 6.9 is my position at t equals 1 second, and 40.1 is my position at t equals 3 seconds. So I've evaluated my antiderivative, the position function, at two values, t equals 3 and t equals 1. And if I find the difference in those values, 40.1 minus 6.9, that's going to give me a displacement of 33.2 units, whatever our unit of distance measure is here. So it has moved 33.2 units, feet, miles. It was not specified in this problem. So essentially, if we go back and we look at part 2, it says find the body's displacement, again, over that same interval, but if I change my initial position. So if my initial condition, I said initial position, if my initial condition is that S is -2 when t equals 0, we would have a different antiderivative. So for part 2, we still have this same position function, 4.9 t squared minus 3t plus c. But my initial condition is that S equals -2 when t equals 0. And so having a different initial condition, what we're going to find out here, changes our problem, and it will change the displacement. So if I plug that in, -2 equals 4.9, 0 squared minus 3 times 0 plus c, we're going to determine that c equals -2. So my position function, S of t, is 4.9 t squared minus 3t, and here we would have minus 2. So if we were to look at our displacement from 1 to 3 units of time, those output values we'd get would be -0.1 and 33.1. And in this situation, when I subtract those, 33.1 minus -0.1, I again get that same difference, 33.2 units. So I've moved to the next page, and we're going to continue this problem doing part 3. So we already did the antiderivative of v, right? The antiderivative of our velocity function with respect to t gave us our position function, which we said was 4.9 t squared minus 3t plus c. So using this initial value condition, we can say that S of t, my output at t equals 0, is S sub 0 or S naught. 4.9 times 0 squared minus 3 times 0 plus c. So simplifying that, we get that S sub 0 equals c. And in this situation, my position function, S of t, is equal to 4.9 t squared minus 3t plus, instead of c, I'm going to write S sub 0 or S naught. So if we evaluate this from t equals 1 to t equals 3, S of 1 and S of 3, what that gives me is 4.9 times 1 squared minus 3 times 1 plus S sub 0, and 4.9 3 squared minus 3 times 3 plus S sub 0. My output values here are 1.9 plus S sub 0 and 35.1 plus S sub 0. So if I go to find the difference between these, 35.1 plus S sub 0 minus 1.9 plus S sub 0, and I subtract those, again, I end up with 33.2. And that is units of measure.